So I would like to talk to you about some research that I have done over the course of the last couple of years. And before I will describe some details of the papers that I wrote with my collaborators, I would like to start with a little experiment, even though we are at a Center for Theoretical Sciences. But I'm a theoretical physicist myself, and my experimental competences are virtually non-existent. So I would like you to take you to a trip of imagination. So imagine that you are holding a bunch of spaghetti in your hands, like that. So now let's think about those strands of spaghetti as of trajectories of material points traveling through ordinary space. Following the first law of motion by Newton, we know that in the absence of a force, each particle will follow the natural trajectory, that is a straight line, x exemplified by those strands. All right, but now, in a slightly different way, we can twist it. And if we twist it, a nice shape is forming. This shape is a hyperboloid, but it's built of straight line. And now imagine two particles starting from the narrowest point of this bundle. And even though they start in parallel directions, as time goes by and they travel along their trajectories, the distance between them increases, which means that we can have motion, a natural motion, which starts out in parallel directions. And even though if we are on a negatively curved manifold, the distance between the material points traveling without an external force increases. And this is a little magic that I'm going to put to use in the context of multi-field inflationary models. So I would like to change this little spaghetti story into equations regarding inflationary models. I think that I'm the first one in this meeting to seriously speak about multi-field inflationary models. So I'm going just to start with a simple graph and a couple of remarks about the evolution. So if I think about multi-field inflationary model, I'm going to stick to a two-field model, and I think that you're going to hear about specific outcomes for more than two fields from Sonia Paban later in this meeting. But in the two-field space, what I can have is a certain trajectory that the fields assume during the course of inflation, and this is a line in this space. Now, let's talk about the perturbations. We heard that in the single field inflationary models, there is just one scalar perturbations. Clearly, here we have two, and it is very convenient to describe them in two directions. So the one direction is along the inflationary trajectory, and these are the adiabatic perturbations that naturally become the curvature perturbations at the end of inflation. And we've got another direction that I will call entropic direction. These perturbations are not directly related to the curvature perturbations that we see in the sky, unless there is a coupling between the two. They would source the isocurvature perturbations, but nonetheless, if there are certain conditions met, they become the source of non-adiabatic pressure that feeds the curvature perturbations, as we heard about in the previous lecture. So the quantity of interest to me will be the mass of this entropic perturbation. On super Hubble scales, I could write this mass squared in Hubble units in the following way. So first, this is the mass of a field, as in any Lagrangian, a double derivative of the potential will give me the natural mass parameter. But there is another complication here, because first, I've got something that's proportional to the square of the rate of turning of the trajectory. So This trajectory in the field space evolves subject to some forces coming from the potential. If there was no potential, there would be a natural motion of the field, and the fields would follow a geodesic line. However, if there is a potential forcing a deviation from a geodesic line, the fields turn away from the geodesic line, and this is the rate of turning expressed in Hubble units. And then eventually, there is the last part here that it can be written in the following way. So first we have the slow roll parameter that we heard about previously. Then we've got the Ricci curvature of the field space, and then there is the Planck mass squared. So essentially, if we think about how it is described in terms of the field velocity, so I would like to say that I could describe it as 1/2 of the inflaton velocity, which I define by capital Phi, divided by the Planck mass squared and the Hubble parameter squared. Now, what can we infer from that? I told you that I was interested in manifolds with negative curvature. And you see that if the curvature is, of the field manifold is negative, there can be a negative contribution to the mass of the entropic direction. And if I have a scalar field whose mass squared is negative, that's a clear sign of destabilization. So now with Sébastien Renaud-Petel, we thought about a simple model that would embody this idea. So I would like to say a few words about the principal construction and the basic notion. So we came up with a minimal Lagrangian like this. We've got the phi field that's intended to be the inflaton, and I'm writing the kinetic term of that field. It is non-standard because it contains an effective coupling to a second field that's not supposed to take part in inflation, so I call it the spectator field. And then I've got my favorite inflationary potential, and then I just write down the simplest possible Lagrangian for the spectator field. So I just want to stress, this is the part that describes the dynamic of the inflaton field. That's the spectator. And the two only couple through the kinetic term of the inflaton. And within this model, I can write down what is the curvature of the field space. So it turns out that the curvature of the field space is -4 over this new mass scale, and then it is multiplied by this factor to the power of -2. Now, suppose that I can cook up an inflationary model in which phi is the true inflaton, so this is the only field that's changing. The spectator sits at its minimum of the potential, that it's at 0. And then, if I can arrange those conditions, so chi is equal to 0, then my scalar field curvature is going to be given by this formula. All right, so now I can analyze a little bit this formula for the mass of the entropic perturbation. Now, I assumed that there is no turning away from the inflationary trajectory, so the second term in this budget is equal to 0. And well, there is nothing complicated about performing a double derivative of the potential for the spectator field. So I arrive at the formula that ms squared is given the bare Lagrangian mass of the inflaton, and then I've got -4 epsilon 1, and then I've got h squared times m Planck squared over this new mass scale. this mass scale can be naturally much smaller than the Planck mass, so this means that this coefficient is large, so eventually I can think about the following situation. In a typical model of inflation, the inflation starts out rolling very slowly, and then it increases its velocity as it approaches the minimum of the potential. So that means that as inflation goes by, this second term is going to increase in magnitude and eventually has a possibility to compensate this mass term from the Lagrangian. So possibly there is a critical value of epsilon1, which is given by 1/4 m squared over h squared and then m squared over the Planck mass squared, at which the mass of the spectator field goes negative. So if that happens, I've got an instability. The perturbations of the entropy, the entropic perturbations increase exponentially, and this means that there is some catastrophe happening in the course of inflation. So if nothing prevents this growth of perturbations from happening, I very quickly make the universe very inhomogeneous because the perturbations grow like crazy, and I am somehow compelled to say that this is a very good possibility for the inflation to end. So is this a danger that your typical inflationary model should take into account? So we try to address this issue in another paper written with my students and with Sébastien Renaud-Petel and Vincent Venel. We first started by saying, okay, this chi equal to 0 approximation is a simplistic one. In fact, if we think about the evolution of a Fourier mode of the perturbations, it evolves in a background that's composed by classical values of all the modes that previously left the horizon. So there is a kind of a stochastic background that should be taken into account by means of the Langevin equation that includes that noise source term. So we solved the Langevin equation, and our purpose was to see what is an expected deviation of the field, of this field chi from 0, given that it evolves in a certain background, and given that it's sourced by noise. So the answer that we arrived at was that the average value of the square of this field can be written in the following way. So first, this is the Hubble parameter at the critical time, so the time that this mass of the entropic direction becomes equal to 0 squared. And then we've got something that's noted by delta and c, and this is the number of V-folds that elapse between the field first becomes light, and that is the mass of the entropic direction is equal to the Hubble parameter, and the time that it becomes 0. So this is the duration of this field being light. So having estimated what's the deviation of chi from 0, we could go back to this model and to think if this deviation affects the evolution that I described to you before. And the answer was positive, because it turns out that once chi is a little bit shifted from 0, then of course, because all the deviations from 0 are unstable, this deviation grows, and it grows exponentially. And it causes two problems. So the first problem is obvious from the formula for the field space curvature. So if you start with chi slightly away from 0, even though it's very innocent at the very beginning, but chi grows, then you see that you start suppressing the field space curvature, and by that, you start suppressing this negative term here. So this is a negative feedback loop that has a potential of turning off your geometrical destabilization, as we called this destabilization with Sébastien. So this is not a very dangerous thing in the sense that it can be cured, because this just comes from our very simple model. We can refine the model, we can live on manifolds of a constant negative curvature, which is not affected by the changes of the field. But there is a much more profound problem that arises. And it can be described very simply on the blackboard by examining the slow roll equation of motion for the inflaton, but this inflaton, remember, lives in a curved space now. So the slow roll equation of motion reads the following way. We neglect the double time derivative, then we've got the term with the Hubble parameter, and then we've got the force term, but this force term is now slightly affected by the fact that we lived in a curved space, namely there is such a contribution coming from Christoffel symbols. And you see what happens now. If chi increases significantly, this means that the naive force coming as the derivative of the potential gets squashed. And in turn, when we remain in slow roll, this means that the inflaton has to slow down. And if the inflaton slows down, this is another negative feedback loop that feeds into this equation and effectively turns off geometrical destabilization. So after our initial excitement and our realization that the geometrical destabilization offered possibly a new degree of freedom that could affect inflationary models and how they are empirically analyzed, we saw a certain danger. And again, you might say, okay, you told us that the problem with the scalar curvature is fleeting. I can go to a constant curvature space to avoid it. But one thing that we did with our students was we showed that the second problem that I described to you is generic. So there is no way avoiding it, no matter how we change the curvature of the field space. All right. But these are very simple back of the envelope calculations. And we wanted to know if this is really a problem if we model this more professionally. And here comes Tomek Krajewski, who worked at the University of Warsaw and who's doubly talented. Both he's a brilliant physicist and he can perform any numerical simulations that a physicist can dream of. So what we did, we put our model on the lattice, and because this is a rather non-trivial field space metric, none of the existing lattice codes would suit our purposes. So we had to write everything from scratch, and we performed some calculations here on the lattice with 512 nodes in each directions. And I would like to show you some numerical results that corroborate the back of the envelope calculations that I was telling you about. So in the upper right-hand plot, you see what's the root mean squared value of the field. And what you can see here is that as the geometric destabilization progresses and zero, n equal to 0, corresponds to the onset of geometrical destabilization, and then the times go by is counted as the number of e-fold. We can see this exponential deviation of the inflaton field from 0, of the spectator field from 0, and then we see this negative feedback loop. So after it reaches a certain value that's roughly equal to the M scale that I introduced before, we see that this growth of the perturbation stops. And then what happens is that we follow a certain trajectory that's different from the trajectory that we started from. So now the field effectively turned and follows a trajectory along which both phi and chi change. Finally, this is a model that's been described in the literature as sidetrack inflation. This name comes from Sébastien Renaud-Petel group. And this model has a funny feature that it's a realization of an idea of a quasi-single field inflation. So the quasi-single field inflation was first introduced by Xingang Chen with collaborators. So if you have an inflationary trajectory like this in a flat two-dimensional space, so you can see that at every point, if the field proceeds with a constant velocity along this trajectory, this trajectory deviates at a constant rate from the geodesic line. And the model proposed by Sébastien and collaborators was similar, but it realized the idea in a curved field space. And basically, this was an example of something that we cooked up with Sera Cremonini 15 years ago. And the idea is that apparently the trajectory is a straight line. However, in a field space, you could have a situation in which, at least optically, the geodesic line deviates from that straight line at a constant pace. So that is sidetracked inflation. Sidetracked inflation leads to interesting phenomenology, especially that it corresponds to model with a reduced or even imaginary sound speed that has its own implications for non-gaussianities. But this is not my story, so I won't be telling you anything more about that. So what we conclude here is that by performing rather exhaustive analysis of the phenomenon of geometrical destabilization, we conclude that this is something that really happens, but it is not a catastrophical phenomenon that is capable of ending the inflation or ending the inflation or even enhancing the curvature perturbations so much that they could produce, say, primordial black holes. This is a fleeting phenomenon that just serves as a kickstart for a different phase of inflation. What we also can see is that in different patches of the universe, once we start with random initial conditions, as geometrical destabilization proceeds, we can see certain patches form because the field randomly chooses one of the directions, left or right, corresponding to chi equal to 0. So some patches correspond to the positive and some correspond to the negative values of this spectator field. So we can see that there are some patches formed with the amplitude of the chi field, again, roughly of the order of this m scale, and the size of the Hubble radius. And what is also interesting is to follow the distribution of the values of chi across all points on the lattice. We see that we start with all the points on the lattice having chi very close to 0, but when the geometrical destabilization is over, this line bifurcates into solutions with negative and positive values of chi. So eventually what we predicted in this oversimplified Z2 symmetrical model is that we have some domains which are separated by domain walls. Of course, if we further complicated the models, we could possibly get rid of the domain walls. All right, does it mean that the idea of geometrical destabilization is dead? So we invented it, we killed it. I mean, it's all in our backyard. I would say no, because it has other consequences that I would like to tell you about. This is a part of the project that was started with a very good student of mine, Michał Wieczorek, and in collaboration with Tomek Krajewski. And this is about studying inflation in alpha attractor inflationary models, and more specifically the T models. So I would like to write down the model first. This is a supergravity model that's described by the Kähler potential and the superpotential, but it turns out that once interesting degrees of freedom are specified, this closely this is very reminiscent of the models that we just discussed. So the class of models that I'm talking about was proposed by Carrasco, Kalosh, and Linde. So the Kähler potential goes like this, and there is a logarithm of the modulus t minus t bar squared divided by 4t t bar. And there is also another superfield S. And we've got a superpotential that is parametrized like this, and then we've got something like this plus multiplied by the S superfield. So once this, I said chiral superfields. These contain scalar degrees of freedom, and from now on I will be only interested in those. And see the scalar degrees of freedom in S are stabilized. So I'm left only with the 2 degrees of freedom that live in the T modulus. So once I write down the Lagrangian describing that model, it reads the following way. So first, I've got a kinetic term for one of the scalar fields that corresponds to the real part of the modulus, and it has a non-canonical form because it's multiplied by a function of another one. Then I've got the kinetic term of the degree of freedom that corresponds to the to another direction in the modulus, and then comes the potential, and the potential can be written as this mu scale, which is alpha mu squared, and then this is the hyperbolic cosine that takes a rather complicated form, but nonetheless it boils down to an understandable analytical formula. And here I've got the power of n, and this is multiplied by the hyperbolic cosine on beta chi divided by 2 over beta squared, where beta is a square root of 2 over 3 alpha 1 over m Planck squared, m Planck, I'm sorry. So I should write m Planck squared too. So now, why was this class of models introduced? First, you see that there are 2 free parameters, mu and alpha. So mu gives you the overall scale of the potential, that is the inflationary scale, while alpha gives you effectively the tensor to scalar ratio, and you can regulate this prediction by changing the value of the parameter alpha. And also this model was very celebrated because effectively, if you think about this potential in the chi equal to 0 limit, it gives you something very reminiscent of the Starobinsky inflationary model. So, okay, I think that we were the first to notice that this model is first intrinsically a 2-field model, and then that it contains a kinetic term for the inflaton field that tells you clearly that you live in a negatively curved manifold, because what you have here is that this scalar field curvature here is minus 4 over 3 alpha. So in the interesting regime that alpha is a very small parameter, and this is clearly admissible by the CMB data, we could have a situation in which the curvature of the field space is large and negative. All right, so does it mean that I can have geometrical destabilization happening in the course of inflation? The answer is no. The answer is no, because in this specific class of the models, the slow roll parameter, the first slow roll parameter is proportional to alpha squared. So this means that once alpha is made very small, the product of the field space curvature and epsilon1 that enters the mass of the entropic direction will be also very small. But this is not the end of the story. And that's because as inflation progresses, the slow roll parameter goes to 1. So we should expect something violent but interesting at the end of inflation. So with Michał and Tomek, we set out to study this phenomenon. This wasn't an entirely easy thing because of a different phenomenon that happens at the end of alpha attractor inflation that was first described, I believe, by Mustafa Amin and Kaloyan Lozanov in 2016. And this involves the self-excitations of the inflaton field. So let me briefly recap what they found and how our findings correspond to theirs. So I'm going to erase this part to draw a little graph showing you how the potential of this model looks like. So here we've got phi, our inflationary direction. We proceed in the regime that chi equals to 0. And then the shape of the inflationary potential is this one. So it has a plateau. It has a dip that's modeled by a monomial. And the entire single field description is proportional to the hyperbolic tangent to the power of 2n of the argument of beta modulus of phi divided by 2. And we see clearly first that there is a plateau, and then as field rolls down the potential and falls into the minimum, we have a change in the convexity of the potential, and that means that we change from the regime of the negative mass squared for the inflaton to the positive mass squared of the inflaton. And during the first oscillations, as the field is trapped at the minimum of the potential, that leads to a self-resonance of the inflaton field. So what Amin and Lozanov studied and found is that if we think about the barotropic parameter, that's the ratio between the averaged pressure and energy density. So as we saw yesterday, that when I have a field that oscillates in a monomial potential, I would, and this monomial potential is something like phi to the power of 2n around the minimum, I should expect the barotropic equation, a barotropic parameter in the equation of state, that's given by this formula. However, by performing lattice analysis, Amin and Lozanov found that in the course of a couple of e-folds, the excited perturbations behave in such a way that this barotropic parameter changes to 1/3. So I said a couple of e-fold, and this is for n larger than 1. So on top of that, there is the phenomenon that I was alluding before, namely, as inflation approaches its end, epsilon1 goes to 1. So now I have also a very unstable entropic perturbation. And with Tomek and Michał, we performed a lattice calculation. And in this lattice calculation, we first, again, wrote our own code because the existing codes weren't able to handle non-canonical kinetic terms. And in the first round, we put our code on a laptop, and then we improved this a little bit, putting this on a supercomputer. And no matter what we did, we came up with the following result for the barotropic parameter. So if I think about the evolution of the barotropic parameter as a function of the number of e-folds. So I know that it can take values from between 1 and -1. -1 is characteristic of an inflation. So what we found was that this oscillated wildly and then seemed to approach a value consistent with 1/3. And this all happened in the course of a fraction of an e-fold. So like in the weakest case, this was half of an e-fold for the parameters for the alpha, which was equal to 10 to -3, and we also considered smaller alphas. So we see that this destabilization is much stronger than the one caused by the self-resonance of the inflaton. And it also has a potential of reheating the universe. And by reheating, I mean that the equation of state is that of radiation. So the problem with our analysis, both on a laptop and on a supercomputer, is that this instability is so strong that no matter what we did, we couldn't resolve this instability once it kicked in. So I can only tell you that our predictions seem to be approaching 1/3, but we don't see any reasonable computational means by which we could fully address this question and tell you precisely how to resolve this singularity for such small values of alpha. But one thing that we are sure of is that we have a situation in which we copiously produce entropy perturbations, mainly entropy perturbations, that then feed into the adiabatic perturbations, and we obtain, at the end of alpha attractor T-model inflation, a universe that's highly inhomogeneous. And because it's highly inhomogeneous, this means that there is a chance that there are gravitational waves produced out of the scalar perturbations in a manner similar to what we had before. However, the equation that we need to analyze is this. So we take the equation of motion for the gravitational waves that has a source. And this source is the energy momentum tensor. And the energy momentum tensor in our case can be written in the following way. So it mainly comes from the gradient term. So this has this cosine factor, and then we've got the gradients of the phi field. And then it's got the gradients of the chi field. So because in our previous analysis, we were able to solve the equation of motion for the perturbations, so we had those ready, we could treat them as a source for gravitational waves and to calculate what will be the amount of gravitational waves at their frequencies in our model. So the result that we get is the following. For a particular choice of n equal to 1 and alpha equal to 10 to -3. And we see that when we are at the end of inflation, so this is roughly this curve, we see that we are at the level of something like 10 to -23 in the participation of the energy budget by the gravitational wave. So this is very consistent with everything that we knew before. And then immediately after this, the instability kicks in, we have a very large growth. And the growth is so large that it can even has a potential to violate the BBN bound, namely the bound for the number of the relativistic degrees of freedom in the early universe. Now, again, the question is if this last line is real, because if it was, then it would just invalidate this model. However, this is precisely on the verge our inability of the resolution of the perturbations. So I'm showing this only for the illustrative purposes, and in the paper where we are expected to report only the truth, you see that this last line is missing because there is also a possibility that the finite lattice size effect also kick in. So, but what I want to stress is that the instability causing the amplitude of the gravitational waves to grow does not seem to stop. So to conclude my presentation, I'd like to say that the negative result is that we saw that the geometrical destabilization phenomenon that we devised with Sebastian is not such a universal thing as we thought, but nonetheless it can have profound consequences for the description of the reheating in models that exhibit a large negative curvature of the field space, and that this instability in such models, and we know that there are existing models seriously taken by people like alpha attractor T models of inflation, that in those models we have a possibility of ruling out these models when they predict too large amount of gravitational waves. Thank you.
Time for some questions. Yes. Is there a microphone there? Yeah, please use.
I have two questions. One question is, omega is equal to 1/3. If n is equal to, let's say n is equal to 3, it will be omega is equal to 1/3 again?
If n is equal to, yes, if n is equal to 2, then...
No, I'm not considering 2. I'm considering n is equal to 3, if I consider. It will be omega is equal to 1/3 then?
You mean here?
Yes, yes.
All right, so 1/3 is going to be obtained for n equal to 1, which is the quartic potential, and the fact that the scalar field oscillating in a quartic potential produces a radiation-like equation of state is, something that's known from prehistoric times, I would say. Brandenberger had it in one of his first papers on reheating. And that's right, that's right. I mean, like, if we take n equal to 2, even without the production of instabilities, yes, that happens anyway, we would have the equation of state that of radiation, yes.
Yes. And another question is, for this case, potential has a negative curvature. So when you calculating this gravitational wave spectrum, so how do you evolve your perturbation? You are initially, what is your initial condition? You are putting the Mann-Davis vacuum, or you are putting the other vacuum?
Okay, so the procedure of imposing initial condition is something that we had to give some thought to, because as you notice, the modes are unstable outside the Hubble radius. Yes. So we impose the Bunch-Davies initial conditions when the modes are still inside the Hubble radius, when they're quite immune from this negative curvature effects. In this sense, we impose the Bunch-Davies initial conditions for the modes when the k-square terms dominates over all other terms in the equation of motion, so they are possibly safe.
For your case, your momentum k mode is very small mode you are considering. That's why you are considering this negative mass effect is not affecting your Bunch-Davies vacuum. Is it your answer?
Yes, so because the physical momentum gets redshifted, once we go to earlier stages of inflation, we can have the momentum factor dominate, and then this is...
I'm talking about the initial one, not
yes. So, yes, so then for the initial conditions, this is completely irrelevant.
Thank you.
Okay, Koushik, other questions for Krzysztof? Yes.
I have a quick question. When you're writing down the Lagrangian over here, you said something to the effect of alpha attractor as a two-field model of inflation. Did I hear that correctly? Or I guess I'm wondering what that means exactly. Like, is it possible to select initial conditions for phi or chi such that the equations of motion just keep them at 0 and then all the dynamics is in just one of the two fields?
All right, so when you look at Carrasco, Kalosh, and Linde and all the subsequent story of alpha attractor inflation, so how this is treated is that you observe that this potential has a natural minimum at chi equal to 0, and that the mass associated with the chi field is typically much larger than the Hubble parameter. So you might be compelled to say, okay, so this is the end of the story. I'm effectively in a single field inflationary model. And I would say that this is true until the instability at the end of the inflation kicks in. So I am allowed to consider the evolution along chi equal to 0 line until that negative entropic mass squared becomes important at the end of inflation.
Are there any other questions? Krzysztof, I had a simple question. Are you saying that the gravity waves are induced by the scalar fields themselves, the background scalar field themselves? Is that what is being said there?
No, so this is all about the perturbation of the fields, okay, which I probably hid in the lousy notation that I used, because chi and phi here were meant to represent mainly the perturbations because they are gradients. Okay. So I mean, this refers to the total value of the field, not the background value of the field.
I understand. Thank you. Okay, if there are no other questions, let's thank Krzysztof again.